We have historically always built software that's functional but not secure. This really is a shift in our industry that we need to have, where security needs to be a part of the actual design, and not just something we add on later as an afterthought. Think of it like building a house or a car. If you forget about the windows and the doors, and you then have to re-engineer them afterwards, it's not going to be as safe. Software is no different. So as part of the requirements traceability matrix, we can have must have this drop down, must be able to perform this action, and then we have the security requirements. If they're part of the design, the software will be more secure. And the more complex software is, the more lines of code that most often has. It's common to have millions of lines of code. I think at least Windows 7 and 8, I don't remember 10, have about 50 million lines of code. And even after doing rigorous software testing, it is still common to have about 1% of vulnerabilities in that code. But remember, vulnerability doesn't mean risk. You still need your threat. If the vulnerability is something that can't be exploited, it doesn't really matter that much. But remember when I talked about the IM programs we're using now? 2 out of the 7 most popular today were actually secure enough, meaning the other 5 are not, because they were designed for functionality. So now that we have built this awesome piece of software, we need to obviously assess it and we need to test it. And this is also an iterative process, and something that should be done throughout the software development lifecycle. Static testing is just testing the code passively. We do not run it. This will be our walkthroughs, our syntax checking, and the code reviews. And all we really do is we look at the raw code and we look for common security issues, practices, function, libraries, anything that we use that's known to be inherently unsecure or has to be implemented in a certain way to make it secure. For this, there are hundreds and hundreds of different tools that you can use to statically test your code, and which you use really depends on the language you wrote the program in. Dynamic testing is actively testing the code while we execute it. We run the program and we see what happens. And we do this to find some of the things that we missed in the static testing. Most code just calls other code to do something. And when you do the static testing, you don't see those interactions. So we need to run it, see how they call each other, see how they work together, and that can uncover some new flaws. But it is also important to remember, a lot of software can run just fine and execute code even if it has flaws. And in our software testing, we use some of the same terms that we use in our penetration testing: white box, black box. And they kind of mean the same, except for software testing. In white box software testing, the tester has full access to the source code, the data structures, the variables, everything they need to see the entirety of the software. Whereas in black box testing, they have no details. They have the software and that's it. They then test the software for the functionality and the security flaws. Remember, in the pen testing, this is where the attacker had full knowledge of an admin, or they had no knowledge about the company other than what was publicly available. See the similarities? And in our software, we use traceability matrices or requirement traceability matrices. And they would normally be similar to this, but obviously much, much bigger. Imagine a giant Excel spreadsheet where the customer has all the requests, all the things that software needs to be able to do. And obviously as part of that, we have the security requirements. And we use the requirements traceability matrix to make sure that the current requirements are met, or at least they are on the roadmap. In Domain 1, when we covered the software development lifecycle, you may remember most software development is an iterative process. And requirements can and will change. And we use the requirements traceability matrix for the specifications that we need from the software, project plan tasks, and all the deliverables documents. And then obviously as part of our testing, when we put out a new version, we make sure that none of the requirements were lost in that software update. Before we actually release our software into our production environment, we go through many different phases and many different teams who test the software. And as part of that, we use unit testing. In unit testing, we test a specific section of the code. That one unit is tested for functionality to ensure it works as we expect it should. In an object-oriented environment, this will normally be done at the class level, and the minimal test units would include the constructors and the deconstructors. And when we have tested the individual units and they are functional as they should be, we can then do integration testing. With integration testing, we verify the different interfaces between the components against our software design. Do each unit we tested in the unit testing actually function together? And we do this to expose the defects or the flaws in the code that prevents them from working together. And this is a progression. We test larger and larger pieces of code together until we confirm that the software works as one unit. And at this point, we are in no way done, which then can move us into component interface testing. We know the interfaces can speak to each other the way we think they're supposed to. How do they handle data passing between them? At this point, we should have a completely integrated system, and we can verify it meets all the requirements we have in our requirements traceability matrix. And then finally, when we as the programmers and the coders, we think we're done, then the business unit or the organization that we're selling the software to needs to test it for their operations. Then they go in and test, does this actually fulfill all our requirements? Can it do what we need it to? And like so much else in software development, it is iterative. We find a flaw, we fix it, then we go through the testing again. Then we find another flaw, then we fix that. And hopefully at some point we're done. Then we do installation testing. Does this software actually work the way it works on our systems on the customer's hardware? I know of large projects where the software was designed and built on a certain set of hardware, but when it was delivered to our company, it didn't work because we didn't have the same hardware. The company we had hired assumed it would probably just work, but it did not. So instead of launching that project on time, we had to spend months and months fixing all the flaws that were there because it wasn't compatible with our hardware. And then regression testing. Every time we update our software, we might have fixed 20 things, but we might have opened other security flaws up. So we look for software regressions, degraded or lost features, or old bugs that we reintroduced. And really it is, for as long as we use the software, a never-ending cycle. Just think of Windows updates. Every month they release new patches, and most of the time they fix 99 problems and break one new thing, or 2, or 5. Then next month, they do the same. And if a really critical flaw is discovered, they put out emergency patches. In most companies I've worked in, we never implement the Windows patches right when they're released. It's called Patch Tuesday, and it's released on the second Tuesday of every month. The companies I've worked in, we wait 2-3 weeks, see what other people report as being broken now, then we do an assessment. Is it worth implementing these patches, or is the new vulnerability so grave that we need to wait a little longer? And here we use proper change management. In fuzzing or fuzz testing, we use lots of different malformed input to either try to gain unauthorized access, or to cause the application to enter an unpredictable state or to crash. If we're able to achieve any of those, the fuzz testing failed. Then we go back and we fix the software flaw. And the person performing the fuzz testing can either enter the values into a script or just use precompiled either random or specific values. And just like in penetration testing, we can also do it iteratively. We analyze how the software reacted to the first fuzz test. Then on the second one, we change the input a little bit. Then we analyze that. Then we change it a little more. That's called mutation fuzzing. And it is, of course, more successful in finding the flaws than just regular fuzzing. All pairs testing or pairwise testing is a type of software testing that is much smarter than simply testing every possible input. And it's defined as a black box testing technique where the test cases are designed to execute all possible discrete, and the keyword here is discrete combinations of each pair of input parameters. And what that really means is, it does not test every possible combination, but it tests the ones that make sense. Because the most common bugs in programs are normally triggered by either a single input parameter or an interaction between parameter pairs. If we have a very simple piece of software, for example, only 3 input parameters. Parameter 1, is the server a physical server or a VM? Is the vendor Dell or HP? And then finally, is the serial number valid or invalid? And the serial number has 5,000 different valid options. If we would test every single combination, we would take 2 times 2 times 5,000. We would have 20,000 different combinations we would have to test. If we'd use all pairs testing, we would have 2 times 2 times 2. Only 8 combinations we need to test. For the 5,000 different options for the serial numbers, we would look, is it valid or is it invalid? We do not care which of the serial numbers it used. And remember, black box testing, we have no knowledge of the software outside of the software itself. And we would also want to do a misuse case testing, because we know attackers don't just use normal traffic. They try to insert code in places where it shouldn't be. They try to get around prompts. They try to gain privileges. So misuse case testing is us acting like an attacker. We go through the steps trying to do what an attacker would do. If we use the example of a simple web form, if someone needs to enter the state they live in the United States, we don't give them 5,000 characters to do so. We give them a drop-down menu. For their phone number, we give them 10 numbers and that's it. But had we not done that, then maybe the state is where we can insert some code that can elevate our privileges, or we can crash the system. And in the end, when we're done with all our software testing, we do a test coverage analysis. How much of the code did we test in relation to the entire application? And because many pieces of software are millions of lines of code, we obviously can't test everything. So we spot check the important areas, we check where we know there might be vulnerabilities, and we look at the test coverage analysis to make sure there are no huge gaps of areas we should have tested that we have not. And then at the end, someone needs to sign off saying, that's enough testing. That is not you. That is someone C-level. And now that we've completed our tests, we need to review what we found out. This is no different than our log reviews. We analyze all the tests and we look at what we need to fix and what we can ignore. And just like the logs, it can be huge amount of data. We prioritize, we act on what's the most important, and the second priority, the third, and we also look at what's okay to leave behind. You can think of this as similar to what we did in a qualitative risk analysis. How likely is it to be exploited, and how bad is it if it happens? If it's low likelihood and low impact, we might just leave it alone and focus on the ones that are higher. As IT security professionals, we do not need to fix everything. We need to fix the important stuff, the stuff that matters.